Okay, so let's start our class of dynamics of structure. And in this class, we are going to talk about the equation of motion for earthquake excitation. And in the same time, I'm going to talk about the free vibration response of single degree freedom system if we have time for this. Okay, now. The contents of today's lecture is going to be related to, first of all, I'm going to explain about equation of motion for earthquake excitation. And after that, I'm going to talk about the dynamic problem statement, knowing what are the input and what are the output and how we can go through it. And then I'm going to talk about important element forces and how they are going to develop. And after that, I'm going to talk about the undamped free vibration response for a single degree freedom system. We're going to talk about the equation of motion. We're going to derive it and use the classical form. And then we are going to redrive it again, but using the amplitude form as we are going to see. Okay, so now let's go directly to the equation of motion. The equation of motion. Equation of motion for earthquake excitation. So this is what we are going to deal with. If we are having a system which is a single story building, for example, if we have a single story building with mass is concentrated at the middle, as you can see. Under ground excitation, so this system is going to move, right? And when it moves, maybe it will be something like this. And we are going to find that there is kind of ground excitation, we call it UG. This is displacement of the ground. And we are going to find that this system is going to move additionally here to this point due to the inertia of the system, which is going to be U only. And the total displacement of this system is going to be UT. We call it UT, U total. Okay? So actually, for our case, if we are going to derive the equation of motion for the earthquake excitation, whenever we have earthquake excitation at the bottom of any building, we're going to apply the concept of D'Alembert's. Okay, if you remember that we have the concept of D'Alembert that we have mentioned before, that we have we have resistance of the system, which is Fs, the elastic resistance of the system, which is the static, and we are going to have a kind of inertia force that is going to be developed for this system if our system is moving under earthquake excitation. So if the excitation is coming in this direction, let's assume this is excitation of the earthquake is coming in this direction. Then we have, this is the earthquake, then we're going to have resistance coming from the system, which is Fs, the static resistance, and we are going to have the inertia force that is going to be developed in addition to another type of resistance that is going to be related to Fd, which is going to be the damping, because we know, as we have explained before, that our system, it has damping resistance based on the material that is this structure is composed of, and based on different sources of damping, as we have explained before. So in this case, we have three different forces that needs to be in equilibrium. So if we're going to have the equilibrium equation using or from D'Alembert's, okay, D'Alembert's. D'Alembert's principle. Okay, in this case, we're going to say that Fi, the inertia force, plus Fd, which is the damping force, plus Fs, the static force or elastic static force, they should equal to 0, right? These are the forces that is going to be developed under the ground excitation. We know well that for F inertia, we are talking about the m times u double dot total. We are in the inertia force, we are concerned with the total displacement of the system. Okay? So m u double dot t plus, sorry, Fd and Fd, I think that it should be Fs here. Sorry for this, this is Fs. Okay. And then Fd, it is going to be C times u dot. C is the coefficient of damping, as I have explained before, and I don't know why it goes like this. And plus, okay, K times u, which is the stiffness of the system, times u, equal to 0, right? So we are going to put our equation again. If we substitute with this u double dot t, it is going to be, as you can see, u double dot ut here equal to ug plus u, right? So this means that u double dot t is going to be u double dot plus u double dot g. We have two types of displacement. One displacement at the base, which is going to be ug, and another displacement which is coming from the structural deformation, which is u. Okay? That's what we call it, ug and u. Both of them, so one component is coming from the ground excitation or ground displacement. So ug coming, if we say this is ug, it is ground displacement. Okay. However, u, it is due to structural deformation. Structural deformation. So we are having like different displacements under the earthquake excitation. So remember well that if let me put it in this color, is better. Fi is related always to ut, yes, it is mass, but it is related to the displacement, total displacement, which is going to be ug plus u. However, Fd and Fs, it is related to what? U only. The structural displacement. Okay? There is difference between the two. If we have, this is the system, and then there is rigid body motion that is going to take place, which is going to be something like this. The whole system is going to move rigidly. Okay? This is ug. There is no deformation in the system. This means that this rigid body motion will not make any deformation in the structure itself. Okay? In this case, we are going to find that there is no elastic force or resistance force, and there is no damping force is going to take place. However, if inertia, yes, there would be some inertia forces, okay, going to be developed. But when we are making our structure here, looking to our structure here, you're going to find that this is the original structure. However, this original structure is going rigidly with ug and deformed by some amount, we call it u. This is the deformation of the structure itself. Okay? This deformation of the structure is going to make or develop Fs and Fd. It is going to be Fs and Fd going to be developed due to you. However, F inertia, it is related to the total displacement. You understand? Okay. Okay. So we can write it something in a form like this, that the rigid body displacement, so we can put it as a note here, the rigid body displacement of the structure produces no inertia forces. Produces no inertia forces. Okay? Sorry, not inertia. I'm sorry, it is not inertia, it is internal forces. Okay, sorry for this. This one is internal forces. We're talking about internal forces here. Okay? So the rigid body displacement of the structure, as I have explained here, okay, the rigid body, this is considered to be like rigid body displacement, produces no internal forces if the system is going to move rigidly like this. But if the system is going to move and make some deformation, there is some resistance would occur. Okay, that's the main difference. Okay. In this case, we can put our system and put the equation of motion that we want to end with m times u double dot plus c u dot plus k u equals to minus m u double dot g. This is our equation of motion. This is our equation of motion. This means that we can put what we call it the effective earthquake force. So we can say that if we have two systems here, for example, this is the first system, we have the mass here, this would equal to, or is going to be equivalent to, same system. Okay, if the system is having kind of ground acceleration u double dot g, this equals to as if the system is having a fixed base, however that we apply horizontal force at the mass level. We call this P effective, which equals to minus m u double dot g, and this is changing with time. Okay, so they are like equivalent. They are equivalent. Okay, so this means what? If we have a mass in a system and the ground motion is there, or there is an earthquake excitation, as you can see it here. Okay, there is a ground earthquake excitation. This means that this system is equivalent to the same system with the same mass, as if the base is fixed and we apply force at the level of the mass. This force equals to minus m u double dot g of t. The interpretation of minus here means that the force applied on the system should always be in the opposite direction of the ground excitation. So if this ground excitation to the right, then our P effective should be to the left, and vice versa. And the mu double dot g, it is related to the right hand side of the equation. It is related to the right hand side of the equation. Okay, so this means that this is the force due to the earthquake. This is the force due to the earthquake. Take care here, there is something important you need to know. Mass is here. What is the meaning of mass? The mass means that the greater the mass, the greater the force. So if we have a mass for one building, and this mass is greater than other mass of the same building structure, then in this case, the building with larger mass would develop more forces, would give more forces or produce more inertia. Okay, so remember that. The mass means that the greater the mass, okay, the greater the effective force, the greater the effective force developed. Okay, and this is the meaning of the M here. The meaning of minus, I'm going to put it here. Minus means that opposite direction. Opposite direction means that the motion of the earthquake is going to develop like opposite P effective, okay, direction. Okay, the minus means that the force acts in the opposite sense of the acceleration. Okay, that's very true. Okay, what we have obtained now for this equation of motion of earthquake, we are going to call it, we are going to call this, it is translational. Translational. Let's make it in green. This is translation motion. Okay, this is translation motion. However, we have another type which is going to be, okay, second, which is going to be rotational. Okay, it is going to be rotational. What is going to be for this rotational? Okay, in this rotational, if we have a system, okay, if we have a system like this, for example, and we have the mass here, we are going to have the rotation of this system under the earthquake. The theta of the earthquake is not going to be translational, it is going to be rotational. So we're going to have theta here. This means that this system is going to respond, let's assume something like this. This is rigid body motion, and then it would respond something like this after that. Okay, so this here, it is going to be theta, and here this is our system. Okay, so there are two different values of, so here we have this value here. This is going to be theta g times h, where the height of our mass from the ground is going to be h. And then the deformation that is going to take place between the rigid body position and the final position, it is going to be titled, or we can give it u. Okay. The total deformation is going to be designated as ut. The total designation is going to be ut. Okay, so we have, this is the case for the rotational one. In this case, we are going to say that this system is going to be equivalent to, okay, this system is going to be equivalent to another system which is going to be stationary at the bottom, as if the same mass is there and it is stationary at the bottom. Okay, so here there is motion here, ground motion. Okay, but here we are going to say that it is stationary or fixed. Okay, fixed base. Okay, means that's stationary. Fixed here means based. Okay, so we can say this is shaking case with rotational, and this is the fixed base, whereas the equivalency is going to take place, and we are going to say that there is P effective is going to be there. P effective is going to be there, and it is going to be changing with time, because our theta is going also to change with time. This is the theta ground. It is going to change with time, right? We do not expect what is the value of it. So in this case, we have this P effective is going to be minus M, the mass, times H times theta, double dot of the ground excitation whenever it is changing with time. Okay, so we have this is the value of the effective earthquake load. So we're going to call this the effective earthquake load. This is the meaning of P effective earthquake load. And based on this, we can say, because as we have said, U total there is, as a function of time, is going to be equal to U of t, which is U of t here. This is due to the deformation of the rod itself, the system itself, plus the rigid body deformation, which is theta g h. So it is going to be h times theta ground motion with respect to t. Okay, so this part, let's put it in another form here. So this part, it's very important to note about this. We call it structural deformation component. Structural deformation component. Okay, this is very important. However, this part is coming from what? It is the rigid body component. Rigid body component. Okay, so we have like two components here. And based on this, we can put our equation of motion. Okay, we can say, based on this, that is M times U double dot plus H times theta double dot G of the ground. This is U total, right? U total here, right? So M times this acceleration term, which giving us the inertia force, plus C times U dot plus K times U equals to 0. This is the equation of motion that we are going to have. And based on this, if we're going to rearrange it, then we're going to have the final equation of motion. M U double dot plus C U dot plus K U equals to minus M H times theta double dot G, the ground acceleration. This is our equation of motion for the rotational case. So we have two cases here. We have two cases. Okay? So first of all, we have the translational case, where that the ground excitation is going to move only horizontally. And we said that there are two components here. One component coming from the rigid body translation of the system, like this one, and the other part is due to the deformation of the system, which is, we call it U. Okay? And we mentioned that it is very important to note that our inertia force is related to the U total, the total deformation of the system. However, Fd, the damping force, and restoring static force, it is related to U only. Based on this, we put our forces on the system, which is based on D'Alembert's principle. And we said that under the earthquake excitation, there is something that is going to be induced in our system. We found that there is mass, and whenever there is a motion, there is inertia. This is D'Alembert's principle, so we put Fi. And we found that whenever the system is moving, there is resistance. We call this Fs, resistance or static resistance. And we found that the material or the system also is producing resistance in terms of damping. So we put damping, Fd. We have three different forces. Then we put it into the equation of D'Alembert's. We want to obtain the kind of equilibrium, Fi plus Fd plus Fs equal to 0. Then we substituted with everything here. Fi, it is mu double dot t, and we decompose it into u double dot plus u double dot g, plus the damping force c u dot plus the static force ku equal to 0. After that, we rearranged our system equation of motion, and we put it in this term, and then we make the equivalency. We ended up with this equation of motion, with this nice equation of motion for earthquakes. We find that it is very similar to the equivalent to the single degree of freedom system, but in the right hand side, other than, or we were using before, dynamic force, P of t, but here we are using ground acceleration and the mass of the system, or ground excitation. And we give the definition of minus and m here. What is the meaning of it? For the rotational, we have in the ground excitation, we have commonly two components, one translational and another one rotational. Okay? This is the common ground motion or earthquake. So this means that the system would go in this direction and might go also like this. The earthquake is going to make the ground make like this. So we want to know what is the equation of motion here. So we said that we are having this our system as a single degree freedom system. There are two components here under the motion, rotational motion. One is rigid body, which is something like this only. And the other one is due to the structure. Two components. So the rigid body is very easy. This is like theta times L gives you this amount, which is theta GH. However, the other one here, it's U of t. This is going to change with time. Okay, so we put it in this way, in this form. So U total of the system or the mass is going to be U of t, structure deformation component, plus the rigid body component. And then we put our system or our equation also, simply principle of D'Alembert's also. So we are going to say that our system is going to be as if it has a fixed base, stationary base, with some force applied at the top. This force is going to be minus mh theta double dot g t, and then there is other forces is going to be developed there. These forces are going to be, as we have mentioned, is going to be the inertia. So we are having the inertia force, which is Fi, for example, and we have Fd, which is the damping force, and we have Fs. So we have three components here, which is these three components here, and the right hand side is going to be the P effective on the system. So now we have the equation of motion and we have the equilibrium. Okay? You understand it? Is it clear for you? Okay. Now let's jump to the next topic, which is the problem statement. And actually the problem statement means that what should we do and what we are going to deal with the dynamic problem in our calculation. commonly we have like 3 different boxes we need to work with, which is the first one is the given, something given for us. The second is what we should find, and the last thing is to get what we want at the end. Okay, so in this case we are going to say that the given commonly for us is 2 main things. Okay, first one, we're going to be given the stiffness of the system, the mass of the system, and the damping coefficient of the system. This is commonly given for us. And the second thing is the dynamic motion or dynamic excitation. The dynamic excitation. And this dynamic excitation, whether it is coming from 2 sources, whether it is coming from the ground, which is earthquake in this case, okay, so we are going to have the acceleration like u double dot g changing with time, or it is going to be like applied force, which is, we call it external applied force. This external applied force is going to be P of T. So this is also given for us. Commonly they are given for us. So what we are going to find here, if we have given this kind of input, what we are supposedly to find? The what? Yes, this is the way how we are going to make it by the equation of motion. But at the end, what we want to know, what is the elements that we want to, or the important things that we want to get from the equation of motion? Yes, displacement and velocity and acceleration. So we have like 3 things: displacement, velocity, and acceleration. These are the 3 main things that commonly we want to have. So from here to here, we are going to use, okay, I'm going to say that by solving the equation. Then what we want to obtain at the end, so what is our main target at the end? Exactly, shear force, moment, axial, so we call this internal forces and straining action. So internal forces, that's very important, which is the shear, the bending moment, axial force, etc. Okay, something like this. Well, that's very nice. Now, what are our tools that we're going to use in order to get from the given stage to the find stage to the to get stage? So here, from given to find, we need to use what? Here, we need to solve the equation of motion at each time step. That's the most important thing. We are going to solve the equation of motion at every time step, and we are going to get u dot and u double dot. Okay? And here, in this stage, between the find and to get the internal forces, we can get, actually if we obtain u, this is the important thing here, if u is known, if displacement is known at the ends of the member, for example, if u is known at each member end, then this means that we can obtain or get the shears, the shear forces, okay? The shears, moments at each member end. Okay, that's very important. I'm going to talk about this now, directly in the next slide. I'm going to talk about this. If you know the displacement at the ends of the member, then we are going to obtain the shearing force and bending moment easily. No problem here. Okay? So now remember this, like this flow chart between what we want to obtain, where that want to get at the end, what the main findings that we should have in our hands, and what are the given that we should always secure in the beginning of the problem. So here, next is, regarding these deformation, I'm going to talk about this, which is this point, which is related to the shears and moments, okay, how we can obtain it from knowing the displacement. As you know, that if we have, for example, if we have member, so we can say that element forces, I would call it element forces. I know that you maybe know it well, but it's a reminder because we're going to use it many times here. So if we have a system like fixed hinged here, and we are going to deform it, okay, deform it by unit rotation here, so we're going to have that our system is going to be something like this. Okay, this is theta here is going to be theta here equal 1 unit. Okay, and we are having the L here. We're having L here, which is the height, and we have EI, which is the inertia of this system. Then, if we are going to have this system, and we are going to rotate this point at the hinge by unit rotation, we're going to find there are moments and shears are going to be developed at the end of this member. So we're going to find that moment is going to be developed here and here, and we are going to find that there is a counteracting shear couple is going to be developed. So we're going to find shear couple here and here is going to be developed. Okay. So what is the value of each one here? The moment is going to be 2EI over L, and here it is going to be 4EI over L. Actually, we should multiply by theta here, but theta is 1 here. We are using 1 unit rotation. So, and the shears is going to be 6EI over L squared, and here it is going to be 6EI over L squared. Okay, and we have L. So this is one of the commonly used members that we're going to have. So what if that we have another member which is commonly used also, which is like fixed element, and we are going to make not rotation, but we are going to make a kind of vertical unit displacement. So here this would be like here, this is like delta equal to 1 vertical unit displacement. In this case also we are having here EI, and we have the same like length and everything is the same. So in this case we are going to find that there is moments are going to be developed. So here we are going to find moment in this direction, and in the same direction another moment here, and we are going to have a couple of shear that is counterbalance here. These shears are going to be of great importance for us when we are going to solve our equations and solve our problems, because at the end we want the shears, okay? Especially shears over moment even, because shears means that commonly we want the force, how much force is going to be developed to make the displacement. So this is the common way for us to solve our problems. Here this moment is going to be 6EI over L to the power 2, and remember that here we should multiply by delta, but delta here means it is 1 because we use only one displacement, and here it is going to be 6EI over L squared. Shears here is going to be 12EI over L cubed, and here it is going to be the same for equilibrium, 12 EI over L to the power 3, right? Very common. And okay, and the last thing is another one also equation that is important for us to have is the case of hinge and fixed here, and we are going to have a unit displacement here, delta equal to 1. So in this case we are going to have our system to be like this. In this case we are going to have the straining actions are going to be at the fixed support only. It is not going to be at the hinge, of course. So we are going to have moment that is going to be developed here, which is 3 EI over L squared, and there would be like kind of shear is going to be developed here. Its value 3 EI over L to the power 3. Okay, I got this. This is very commonly used, especially these three cases. Okay, I'm going to find it many times in our examples. So take care and please memorize these forces and straining actions that is going to be developed. Okay. Okay. Another point that we want to jump into is related to the combination of or combining static and dynamic responses. Combining static and dynamic responses. Dynamic responses. When and when not that we should combine the static and dynamic responses. Okay? So, in general, if we have linear system, okay, if we have linear system, then in this case direct superposition is okay. This means that static plus dynamic would work for us. What is the meaning of this? The meaning is if we have static displacement, okay, then we can combine with the dynamic displacement, for example. But if we are dealing with non-linear system, if we're dealing with non-linear system, okay, direct superposition, so direct superposition is not okay. Not okay. Take care of this. So we cannot say that static plus dynamic response are going to be our answer. We cannot do this. Okay, so static plus dynamic, okay, is going to be wrong. Okay, we cannot do this. Okay, we cannot do this. Okay. So why we cannot do this? What is the main reason for this case? We can write down, or you can write down, or you can not write it, because the dynamic analysis must recognize the deformation of forces to establish the initial stiffness of the structure required at the start of dynamic. The point is, here, for the dynamic analysis, we need to know the stiffness before start for the solution. If we're talking about linear system, the stiffness is constant. It is okay. So we know the stiffness at every time because it's constant. However, if the system is not linear, that it's like there are some changing in the stiffness, the tangential stiffness, this is a problem for us because we need at each time to know what is the stiffness required for the dynamic analysis. So we cannot add, we cannot superimpose the two responses from static and dynamic in this case because the dynamic will be inaccurate. The dynamic would be inaccurate. So if you want to record it like this, because the dynamic analysis must recognize the deformations and forces to establish the initial stiffness property of the structure required to start the dynamic analysis. Okay, can write it, or you can write it when you watch the video at home. Okay, it's okay. So I want to finish with the last part. Okay, so that we are going to have the last part here, which is the most interesting part for us, and it is going to be free vibration response. Okay, so we're going to talk about free vibration response, okay, of the system, and we have different cases for the free vibration. We are going to have undamped free vibration, so we are going to have undamped, and there is damped condition. So we are having two different ways for the solution of free vibration response. So let's start with the undamped free vibration. So we're going to talk about the undamped free vibration. Okay, the undamped free vibration. This is our case for today. Okay, now let's start with the equation of motion directly and see how we can work with this. So first of all, in the common equation of motion, we say that mu double dot plus cu dot, okay, plus ku equal to 0, right? If we're going to talk about undamped system, so which term is going to cancel here? C. Yes, we do not have the second term because it's no damping, right? So the second term is going to be not there. There are not going to be any damping force. This means that our equation of motion is going to be mu double dot plus ku equal to 0. This is our equation of motion. Okay, this is our equation of motion. Okay, so now let's understand what is the meaning of this. First of all, this 0 here means that there is no external forces, applied, right? So it is free. Okay, it is free. And whenever that we vanish, or this term is vanishing, the damping, okay, this means that no damping here, no damping is going to be considered. We're going to assume that our system does not have damping. Okay, and the word free, whenever we talk about the word free, what is the meaning of free vibration? Is initiated by disturbing the system. This means that the system is initiated by disturbing it from its static equilibrium. Okay, this is equilibrium condition by giving the mass. We're going to give the mass initial velocity and initial displacement. So we're going to give the mass, what we call it, u node of t and v node of t. This is initial displacement. We call this initial displacement, and we call this initial velocity. So that's the meaning of what we are studying. Okay? This equation that we are going to analyze now, this equation is first degree linear differential equation, and it is second order because we have u double dot. Okay, and it is homogeneous because the right hand side is 0, okay, with constant coefficient. Okay, if you know about mathematics and differential equation, it's a very common, conventional, classical way of differential equation. We can solve it easily. Okay, so now let's go and solve it. Our mathematicians or our mathematician friends, they said for us that the solution, so we can say that the solution of this equation of motion, the solution of EOM can be given in 3 different forms. So we can say the first form is U is going to equal A cosine omega t. Or another form, which is U equal to B sine omega t. Or another form is U equal to A cosine omega t plus B sine omega t. That's very good. Now let's go and understand. Whenever I say solution of this equation, what do I mean by this? What is the meaning of solution? What I want from the solution? The what? Yeah, the displacement at the end, as we said here. Do you remember? We mentioned here that to find u dot and u double dot. So we want u. In order to solve our equation, we need to have this u. So now, in order to solve this equation, the mathematicians would solve it for us, and then they would give us this. They said to us that we do not have only one way of solution, we have 3 ways. U equal to A cosine omega t. What is A? It's a constant, right? Constant of what? Came from where? Yeah, that's right. It is a constant. Yes, we're going to use it, but in the same time, this constant, whether it is A or B, yes, we are going to develop them from the initial conditions. Do you remember here? We said that we have what? Initial displacement and initial velocity, right? So this means that we are going to disturb the system with initial velocity and initial displacement, and we are going to obtain A and B. So this A and B, you can say A and B, they are constant, and they can be obtained to be defined from the initial conditions. Okay, to be defined from the initial conditions. Okay, and what is omega here? This is what we're going. It is what? Yes, that's right. But we want to highlight that if we're going to use equation, so now you can understand that the solution is 1 and 2, they are A cosine and B sine omega t, but the third solution is the combination of the two. It is A cosine omega t plus B sine omega t. It's the combination of the first and second solution is the third solution. Okay, now let's go and see how we can solve this using the first equation, which is 1. So let's have, so if we use equation 1, what will happen in this case. Okay. First of all, we need to put what is u dot and u double dot, right? So we have u dot of this, it is going to be minus omega a sine omega t, right? This is the first derivative. And the second derivative is going to be minus omega squared a cosine omega t, right? First derivative and the second derivative. Okay, in this case we are going to substitute in the main equation of motion. Okay, substitute in the main equation of motion, which is mu double dot plus ku equal to 0. This is our main equation of motion, right? We have u and we have u double dot here. So we know u, okay, and we know u double dot. So if we are going to put in this equation u and u double dot, we are going to have this final term. Let me put it here better. So we're going, if we rearrange, we are going to find that our system is going to be minus m omega squared plus k multiplied by a cosine omega t. Okay, this would equal to 0. This is if you take a common factor and substitute and rearrange and so on, you're going to find the equation would be like this. Okay, so in this case, from your own point of view, we have two terms multiplied by one another and they equal to 0. Which one that must equal to 0? The first one must equal to 0. So the second one, why not?
Because we need to find constant and a cannot be equal to 0. Or
What about cosine omega t to be 0? So, why there is one of them should be 0 and the other is not? And which one?
I think this is the one which is equal to 0 because the first one is constant.
The what? The what?
The first one?
Yes.
Constant.
Mm-hmm.
So it's not equal to 0 like this.
Okay, actually no, it's counterintuitive also here. The second term, it is changing with time, right? If we say this second term equal to 0, means that there is no motion. There is nothing is going to be there. Every time t, at every time t, this a cosine omega t is going to be 0. This means that the system is not going to oscillate. There is nothing. It will be 0, constant, static. Okay, because the t is changing. However, this term, which is minus m omega plus k, this is okay. We can equate it with 0 and see what will happen for us. Okay, so based on this, we are going to say that our system, in this case, which is minus m omega squared plus k, this is must equal to 0, not this term, not the second term. Why? Because the second term, it has t, time is there. So if we rearrange this, we're going to find omega equals to square root of k over m. This is the most famous equation in dynamics. Yeah, yes, this is the circular, yes, the natural, this is one of the natural property, the natural circular frequency of the system. So now let's like give a kind of definition for this. This is what we call it, the natural circular frequency. The natural circular frequency, and it is going to be in rad per second. It is going to be in rad per second. Okay? So in this case, yes, this omega, this is one of the natural property. Do you remember when I was like talking before and saying that we have the frequency, which is 1 over Tn, and we said that omega natural n, which is n here, it equals to 2 pi over Tn. I think that you know well what is the meaning of Tn from previous lectures, okay? Okay, and from here we can say that Tn equals to 2 pi over omega n. So we have this value. Okay, the word natural here that is going to be used here, why we use the word natural?
Because it belongs to the structure.
We do not what?
Because it belongs to the structure of the structure.
Yes, we can say that because the system like vibrates freely without any external force. So we can put this like this. So that's the meaning of natural. We can write it like this. The natural because the system vibrates. Natural because the system, or because, okay, because the system vibrates freely. The system vibrates freely without any external force. Any external force. Okay? Also because the system is linear, these values are independent of the initial condition. Yes. So this system actually is linear. Do you see any initial conditions here? No. There is U node or V node or something? Nothing. Right? So it does not relate to the initial condition. What is the meaning of this? The meaning that if we have one system and I initiated by U node and V node like 10 and 20 respectively, it doesn't matter if another person initiated with another value of the initial displacement or velocity. It will not make any difference. The system will vibrate like freely with the natural frequency that we are dealing with here. Okay? Understand it? Okay, so also you can write this note, small note, you can watch it also or listen to it. Also because the system is linear, these values are independent of the initial conditions. Okay? Which means that the displacement and velocity. Okay, so now we were using equation 1. Now what if that we are going to use equation 3? We're going to use equation if we use equation number 3. What will happen for our equation of motion? Okay, in this case, we're going to have u equal to a cosine omega t plus b sine omega t, and we're going to have u dot, it is going to be minus a omega sine omega t plus b omega cosine omega t, right? Cosine omega t, that's right. So we are going to use the initial conditions. The initial conditions in general, whenever that we talk about initial conditions, what is the meaning of it? So if we have like here u of t, and here we have the time, which is t, and our system is something like this, for example. So the meaning of u node and v node, okay, so this here, this is u node, which is the initial displacement. At time t equal to 0, this is the initial displacement. And v node, it is going to be the slope at this point. Okay, the slope at this point, which is at the first point here, this is going to be v node. This is the initial, okay, initial displacement. This is going to be the initial velocity at t equal to 0, right? At t equal to 0. So we are going to substitute in the equations, and we are going to put, instead of u here, we're going to put u node, and cosine omega we put t equal to 0, and then get the values of a and b. Okay? This is similar. We're going to use u and u dot because we're going to have u node and v node in each equation and put with t. So we can say by using t equal to 0, then we're going to have u equal to u node and v would equal to, or u dot is going to be v node. In this case, we can obtain the constant a is going to be u node and the constant b is going to be v node over omega. So we have our constants now are known for us from the initial conditions. Okay? So based on this, our equation of motion is going to be then, let's say, so in this case, the equation of motion, which is already this u here, so it is going to be like this, in this form. U equal to u node cosine omega t plus v node over omega times sine omega t, right? This is our equation of motion. This is our equation of motion, right? As you can see, it is, we can call it a nice title and give a nice title. It is a simple harmonic motion. Simple harmonic, it is simple harmonic motion. SHM. SHM. Okay? So why we call it simple harmonic motion? Because it oscillates about the equilibrium. So we're going to find that in our case, this kind of motion is going to be something similar to this. Okay? Okay, if this is t and this is u of t, for example, then it oscillates around the original equilibrium condition. Okay? And it repeats itself. And simple harmonic because we use what? Cosine and sine. Do you remember when I was giving the values or the different types of dynamic loading? I said there is periodic loading and simple harmonic. This simple harmonic means that it can be described with cosine and sine. It can be described by sine and cosine. So this is why we call that our system is under simple harmonic motion. Okay? Okay. This is the the equation of motion. We're going to put this is the would be the last thing, which is we're going to put this form in another form. Okay? And we are going to call the equation of motion is the amplitude form. Okay? So let's go here and put what we are going to give it as the amplitude.
It's time to start another next class.
Next class?
Yes.
At 6 p.m.?
Yes.
Okay, 5 minutes and I will finish. Okay. You have class? You have to move. Okay, so maybe you can? Okay. So it is okay, you can go and you can watch the video. So I want only to finish with the amplitude. We call it the amplitude of motion. Okay, the amplitude of motion. And this amplitude of motion is going to be like describing the relation between the A and B. So we're going to put here U node, and here we're going to put V node over omega. And we are going to assume that this hypotenuse is going to equal the square root of V node over omega squared plus this U node squared. Okay? This is only an assumption. If we're going to look to the equation of motion, we're going to say that it is u node cosine omega t plus v node over omega times sine omega t. What we're going to do simply is, I'm going to multiply here by rho, okay? The total equation will be multiplied by rho, and I will divide by rho also. So I didn't do anything, right? I didn't do anything. But what is u node over rho? U node over rho equals what? It equals to, so u node over rho, yes, equals to what? U node over rho. It is going to be sine. This is going to be called alpha, for example. So it is going to be sine alpha. And this v node over omega over rho, which is the horizontal projection over the hypotenuse, it gives us what? Yes, it is cosine alpha, right? That's the case. We are going to put this u, in this case, we're going to say like this. So u is going to equal to rho times sine alpha cosine omega t plus cosine alpha sine omega t, right? And if you are going to use the trigonometric transformation, you're going to find this is going to be, if we're alpha and omega t, alpha and omega t. So we can put u as rho times sine omega t plus alpha. This is based on trigonometric transformation. Trigonometric transformation. We can put it in this form. Okay? If we use this to be theta, then this equation is going to be u equal to rho cosine omega t minus theta. Also, this is based on the trigonometric relations. This is, we call it the amplitude form, the amplitude form of motion. The amplitude form of motion. Okay? You get it? This is the last thing for us for today. I hope that you understand it, and I hope to see you in the next video with another topic. Thank you, and see you.